So we start. On behalf of the CAPSS Physics Group, I welcome everyone in the 9th lecture of this seminar series. This lecture is being live streamed in our YouTube channel, Nature as We Unfold It. There you can also find the videos of all other lectures we have gone through earlier. A formal introduction of our speaker today will be done by our host Shreya. Once again, I welcome you all and I hope you will really enjoy this talk. Over to you, Shreya. Thank you.
Thank you, Pachita, for giving me this opportunity to host the event. So good evening, everyone. Let me welcome you all to the 9th lecture of the Nature as We Unfold It seminar series of CAPSS. I am glad to introduce our today's speaker, Dr. Shibaji Banerjee. Dr. Shibaji Banerjee currently is an assistant professor at Xavier's College, Kolkata. He completed his bachelor's in science from Calcutta University. He completed his master's from the Presidency College and Shah Institute. He did his PhD from S.N. Bose, Kolkata, under the supervision of Professor Shibaji Raha. He then joined St. Xavier's College in the year 2000, and now he is an assistant professor at St. Xavier's College. Dr. Banerjee has done many interesting works in the field of general relativity, cosmology, astroparticle physics, dark matter, dark energy, and high energy physics theory. Today he is going to talk about Chandrasekhar limit for quark stars. So before spending more time, I would like to forward the mic to Dr. Banerjee, and I would request the audience to keep your microphone off if you are not speaking, and if you have any question, you can type in the chat box or you can ask at the end directly to our speaker. Thank you. Sir, you have the mic now. You can start.
Thank you very much, Shreya, for your introduction. And thank you all the organizers of the CAPSS Research Physics Group for inviting me to this seminar. I would just like to mention one thing, that I have not done my PhD from S.N. Bose, but from Bose Institute, JC Bose Institute itself. So with that, okay.
Okay, sir. Okay.
Okay, thank you. Very good evening to all participants. And obviously, it's indeed a great initiative taken by you to keep the channel of academic discussions live during these trying times. I am personally happy to present today because very long before I was associated with SXC, I was also a member of this forum itself. And that brings back some remembrances, fond memories, and so on. Today, I will talk about the Chandrasekhar limit for rotating quark stars. Okay, so let us begin briefly with the subject of compact stars. Now, as we know, as we are aware of, that these stars, they mostly represent end stages of active stellar evolution. Now, having spent their nuclear fuels, the white dwarfs, they keep the gravitational compressive forces at bay by virtue of the electronic degeneracy pressure. All fermionic systems respond in the same way when they feel the squeeze. However, for neutron stars, the neutron degeneracy pressure by itself is not sufficient to hold up an object beyond the 0.7 mass solar limit, and because their repulsive nuclear forces, they play a much larger role in supporting more massive neutron stars. Low or medium mass star with mass less than about 8 times the mass of our sun will become a white dwarf. A typical white dwarf is about as massive as the sun, but only slightly bigger than Earth, and this makes the white dwarfs one of the densest forms of matter, surpassed only by neutron stars and black holes.
Pardon, sir, but are you showing us any slide? Because we cannot see any slide. So,
Oh, sorry.
uh,
Okay. Okay.
okay, thank you.
Okay, I'm sharing now. Okay, so I think this the screens are visible now, right?
Yes, sir.
Okay, so we begin with the subject of compact stars, and we were discussing these compact objects. Now, if we look at the scenario that a neutron star, well, it is formed during a supernova explosion. It is an explosion of a star that is at least 8 solar masses. And the maximum mass of a neutron star is 3 solar masses. If it's get any more massive than that, then it will collapse into a quark star, possibly, and then into a black hole. We do not know the exotic matter with which the black hole and so on they are composed of, but we can have a hint if it goes through this intermediate stage of a quark star, because quark matter is a more or less well-studied phase of matter. Now, all these compact objects like these white dwarfs, neutron stars, black holes, and quark stars, if you look at the white dwarfs and the neutron stars and black holes, now they are all gravitationally bound. Now, when we say gravitationally bound, we mean that the gravitational energy that binds them is predominantly much higher than the solid state forces that hold our everyday objects together. You can estimate that, and if you estimate that, you would find that these objects, well, greater than the mass of an say small asteroid like Ceres, are all gravitationally bound, right, going up to the level of galaxies. However, if you look at objects like a quark star is bound by strong interaction forces, which are much more dominant because of this very strong interaction between the unconfined or the asymptotically free quarks. So this is the basic difference between various kinds of compact objects, and the quark star is quite a different beast. So if you look at the evolutionary picture of a quark star, it is considered to be the very end product. Well, the standard story is that the fuel of a star gets exhausted, then the core parts they begin collapsing due to their own gravity. Quark core. This is important, that the quark core is spontaneously generated at very high values of density or temperature, and it grows over time, capturing free neutrons. When it captures the quark core, I'm talking about the quark core, it grows over time. When it captures the free neutrons, it dissolves its hadronic boundary and gets into the quark phase. And if the quark matter that is present inside the core is more stable than the normal hadronic matter, then this grows over time over the material composition, nuclear matter surrounding the quark core. And a thin outer layer of comparatively smaller density is also generated outside the quark core, which is very small compared to the density of the core. Now, Witten in 1984, in his very seminal paper, The Cosmic Separation of Phases, have developed this hypothesis that two-flavor quark matter composed of up and down quark matter is not very stable, but if strange quark matter is included, then the additional Fermi well makes the quark matter and the quark material inside the core much more stable compared to ordinary nuclear matter, like say the stable things like iron and so on. Now, there is, however, another possibility. Now, instead of a star which grows its quark core from inside, it can also be formed by clumping of ambient quark matters. Um, so, due to the gravitational interaction, like say, they can draw matter in, and this can let the star grow into a quark star, which we will call a pure quark star. So quark stars might not only be formed from neutron stars, which themselves form from supernova explosions, but they could be also created in early cosmic phase separations, like in the microsecond era following the Big Bang. And if these primordial quark stars can transform into strange quark matter before the external temperature and pressure conditions of the early universe rendered them unstable, they might become stable. And if the Bodomer-Witten assumption holds true, so such primordial strange stars could survive the disco. And this possibility is enhanced if, by the droplets of strange quark matter known as the strangelets, or these primordial strange stars, which we have discussed. Now, if you look at the mass of a quark star, then in our the concept of Fermi energy is very well known from the study of electronic structure in metals and semiconductors. Due to this Pauli exclusion principle, the electrons, which are essentially free, the electrons are essentially free, even though they are confined in the bulk of the metal, they cannot all club together in the ground state due to the exclusion principle, and they stack up even at zero temperature. The Fermi energy is the difference in energy between the highest and the lowest occupied single particle states in the quantum system of non-interacting fermions at absolute zero temperature. On the other hand, in thermodynamics, the chemical potential of a particle species is the energy that can be absorbed or released. Okay, so it is in a chemical reaction or phase transition. So when both the temperature and pressure are held constant, at zero temperature they're essentially the same. They're same in zero temperature. Apart from some factors which include the statistical degeneracy factor, which we call here the G, and this factor of 4, if you're worrying about it, that we are having this energy density in the left hand side, and in high energy physics the length is measured in inverse energy dimensions, so they match up. So this is the relation between the Fermi energy and the chemical potential. Now the chemical potential for a star which have n number of fermions, we assume like that this star is actually a spherical object containing free quarks, asymptotically free quarks confined in a bag, and bag which limits them because it's an hadronic, it's like a very large hadronic bag, it's like a very overgrown nucleus, and it contains these asymptotically free quarks which are trapped by this energy called the bag energy, so that the free quarks are not observed in the outside universe. So this chemical potential is related to the number of fermions and the radius of this spherical star in this way, into the power 1/3 by r. So these are the essentially two very simple ingredients that gets into the model building of a pure quark star, which consists of a bag, hadronic, very large hadronic bag, a superparticle kind of thing containing these asymptotically free quarks. So in this model, now in physics, when we do this model building, we are in the initial phases, we are already almost always we are talking about a spherical cow. Well, things can seem to be quite unrealistic, but we try to capture the essence of the fact without worrying about any spurious problems which may come along, like the specific equation of states and so on. So this is essentially that kind of a very simple model. So the total mass in this model is the Fermi energy times the number plus the volume into the bag energy density. And using these previous two expressions, we write it in this way. Now, the presence of this factor 1 by r over here and r cube in this term allows us to extremize the mass. So this we want to check whether it will lead to a stable configuration. So we make use of the Landau principle to minimize its energy, just like we did for the white dwarfs. And when we do that by extremizing, we find that this Fermi energy density is related to this bag energy as EF equal to 3b. And substituting for the expression of mass, we get the mass is equal to 4bv, which is 16 by 3 pi b r cube. So we get both the Fermi energy of the particle as well as the total mass as functions of b and r. The mechanism of confinement, if you look at, then this mu has to be b by n. So which means the chemical potential scales as the inverse of 1 by n. So this mimics the confinement of mechanism of confinement, that the quarks cannot come out their hadronic bags, because when we try to do that, when we try to reach the state of this zero density, like the mass of the isolated quark becomes infinitely high. So the vacuum is unable to support it. This model is called the density dependent quark mass model. It is an empirical model of emulating the confinement. It was first discussed by Yogesh Poti and then subsequently developed by Fowler and Raha. It's a very interesting model, which you will see that it can lead to the correct mass for this kind of a system of quark star. So for a system of quarks at zero temperature, the energy density tends to a constant value, while the mass tends to infinity as the volume tends to infinity and the density tends to 0. So the effective mass is the 4 times the chemical potential. Now to this we must add the gravitational energy of the particle, and which is just the effective mass put into the expression for the, in this case, the Newtonian gravitational potential. And this total energy, the Fermi energy plus the gravitational energy plus the confinement energy, so if you minimize them with respect to the n, the total number of quarks, then we find an expression for the maximum radius possible for the quark star.
Sir, excuse me, sir. I'm extremely sorry to interrupt, sir. Sir, can you please repeat from last 2 slides? Actually, otherwise I will completely lose track.
Okay, but well, fine.
I'm extremely sorry to interrupt you, sir.
From here?
From the previous slide.
From here, I suppose.
Yes, sir. That will be.
So we have, so we have expressed the total mass in terms of the Fermi energy and the confinement energy, and then we have minimized to find the relationship between the Fermi energy and the back constant, and then we then we got the expression for the mass. After we have got the expression for the mass in terms of B and R, we found that the chemical potential is B by N, so it varies inversely as the 1 by N, and so this effective mass is the 4 times effective mass of a particle. The quark inside the star is the 4 times the mu. So when you try to reduce the volume to infinity, the density tends to 0 and the mass becomes infinite. So this mass we cannot observe. So we say that the mechanism of confinement is mimicked by this density dependent quark mass model. This depends on the number density in the inverse way. And then we include the gravitational energy of the particle by substituting the effective mass in the expression for Newtonian potential energy. and then we minimize the total energy, which is the Fermi energy, gravitational energy, and there is also the binding energy term, and we get the value of R which maximizes, the maximum value of R which minimizes this energy. So the Landau principle is operating here, and we get this expression for the R max. Now, if you look at the expression for the R max, this contains, this is written in natural units. So H factors of H cross and C are not here. They are there. So it depends essentially on fundamental constants like this H cross, E, and the Newtonian gravitational constant G, and the fundamental mathematical constant phi, and also the phenomenological constant P. So this is an expression, this is a pure analytical expression in which one can express the radius of a quark star in terms of fundamental constants. If we raise the back constants to the status of a fundamental constant. Now this back constant, it was a phenomenological constant of QCD, but now this seems to express a fundamental property of these very novel states of matter. So we can regard it as such, and we can see what this leads to. This is the expression for the R max. And from the R max, just using the simple Euclidean volume formula, you get the mass 16 by 3 pi d R cube max. So very simple formula for the maximum mass of a quark star object. Okay, so while this is indeed elementary physics, the real insight being hidden into the density dependent mass model, because we have not used any specific assumptions so far about even how much UDNS matter is present in the star, but then we have calculated the values of these R max, M max, and N max, and we tabulate this for various values of the back constant. So these are the results. For the value of the b to the power 1/4 as 145 MeV, or b as 145 MeV to the power 4, we find that the M max is 1.54 solar mass, which is valid for low mass quark stars. We have, and if you vary the back constant to other values, this was actually the most favorable value of the B which was found from experiments. So it gives the correct range of the mass for this low mass quarks. So we see that there is actually a limiting mass for these quark star objects, although they are bound by very different mechanisms compared to this other class of compact objects. So beyond this, they would be gravitationally unstable. And we found that this depends only on universal constants, except that you take the bag energy to be elevated to the status of an universal constant in its own right, because it also represents the difference between the non-perturbative and perturbative vacuum of QC. It can be seen from these equations that the physical radius R max, now corresponding to the maximum mass as well as the maximum mass itself, they are independent of the number of quark levels. So this is a result which is agnostic of the number of quark levels. In fact, we have verified that there is almost no difference in Nmax between the cases with either 2-flavor quark matter or 3-flavor quark matter. So in turn, this implies that the assumption of massless quarks does not materially affect these results. We started with massless quarks, then they gained this mass through the density dependent interaction, and they describe the maximum mass quite well. Well, it's true that the methods that we apply here are very pedestrian, but the limits, they agree very well with those found with the help of numerical solutions of the TOV equations as well. So this radius is more than 2 times the Schwarzschild radius of the corresponding objects. So here we have not stepped beyond the Newtonian limit, and that is more or less justified because the radius is quite large. But we will find that this assumption will not hold when we consider a rotating quark star. Now we include the kinetic energy per particle into the rotation using this very simple formula, where we take this is essentially a special relativistic formula. This is the frequency of the rotating star is here, and you have this special relativistic factor minus the mass due to the object. So we extract the kinetic energy from the total energy due to rotation and the frequency. However, now we have to consider the fact seriously that the star is not an Euclidean sphere. That is, its volume is not equal to 4/3 pi f cube. So we take this into account by calculating the dV using the metric valid for spherical polar coordinate systems. We take it from the Schwarzschild metric and we calculate the volume element from there. So when we find the maximum mass, we use the expression. We assume that the star is compact and it affects the space-time, which in turn affects the geometry of the star, and therefore we have to make use of the general relativistic volume element, which carries this square root of root over of g mu nu, the metric, as the signature element. And other thing that we have to be aware of is that the frequency that one observes. In this figure, we calculate the frequency we minimize again, and we find the relationship between if we vary the frequency, and we calculate the mass of the quark stars. So this is more or less the result. Now the frequencies, we have to consider the effect of redshift, gravitational redshift near the surface of the star. These stars are compact, and now we are taking this general effect, and we can see that indeed there is an effect, because the redshifts which occur near very compact objects will affect the observations of a faraway observer. So these red dots, which show a monotonic increase of frequency, they are visible to, and these are the actual frequencies of the star, but the outside observer who is remotely situated will observe the redshifted frequency. Now, how does this relate to the actual data on, say, the pulsar periods which have been discovered recently? So in order to see that, we will look at a table. So we have selected various pulsar objects with high frequency of rotation which have been recently discovered. So these are the pulsars, and here in this column we tabulate their masses. We also have we know the spread in the frequency which have been observed. So we try to look at how these pulsar masses fit into the picture of the rotating quark star. So in order to do that, we do a chi-square analysis, very simple chi-square analysis, where the value of the chi-square is given. Here is the difference, it's the ratio, difference of the calculated masses and the observed masses taken from the tables, and the chi-square is then minimized. So this chi-square is minimized with respect to the value of the back potential, and we can see that it has a minima near about 136 GeV to the power 4 for the value of B. And then we explore the space of the masses varying with the frequency, and then we also plot these masses together with our analytically calculated values. We eliminate some variables, like, so we exclude the star PSR J1311 minus 3430, because it has a very large uncertainty mass, and the chi-square is calculated after rejecting these data. We nevertheless plot the data, but chi-square is calculated on the basis of the data, which doesn't show us such a large spread in this. So here is the results that we obtain. Now for each chosen value of the back constant, which are 130, this one is the value which minimizes the chi-square. We have plotted this line in black. The other values are 145, 165 and 185, and the various objects which were shown in the table, they are plotted on top of this plot. So we find that the limiting mass, well, it remains almost constant. It doesn't change much with frequencies as long as these frequencies are low. But as the frequency nears about 300 Hz, the kinetic energy becomes sufficiently high to be taken into consideration for the calculation of the effective mass. So as a result, Mmax, it starts increasing gradually with frequency, and near about 600 Hz or so it increases very fast. Now beyond us, this instead of increasing in a monotonic way, this curves back, because these observed frequencies, they start falling with the increased gravitational effect as the masses, it becomes more compact. So this provides a limiting value of mass for each value of the back constant, and several numerical models and simulations indicate that the value of the back constant for stable quark matter systems lie within the range of 135 MeV to the power 4 to 162 MeV to the power 4. So we have used these values to generate the plot. And the range of this back constant corresponds to observed frequency ranges of 677.4 to about 1052.6 Hz. So as a consequence, the span of this 677.4 to 1052.6 Hz addresses the possible upper bound of the observed frequency of quark stars, which are of the millisecond order. Now, in contrast, these values of the back constant agrees with the value work of Gaur-Gulhan et al. And so on. So for example, according to the best point of our chi-square analysis, which is at 136.5 MeV to the power 4, the maximum value of the observed frequency of quark star is 747.7346 Hz, and it agrees with the observational evidences of very fast spinning pulses. However, that is not the actual frequency, that is the observed redshifted frequency, and the actual frequency for this case is like more like 1248 Hz. So in this other plot, we show the variation of the radius, maximum radius in kilometers versus the frequency. So all these show the same behavior near the frequency for various values of the back constant. This is the curve which we have extracted, and in this graph we show this variation of the number of particles corresponding containing this star with the frequency, which these curves are more or less scalable. And in the other case, the same limiting frequencies we get. And in this other panel, we show this quantity R max by R source channel. So we have studied this parameter because we need to know whether whether the material of the comprising the quark star in this model can actually develop into a black hole. Now this ratio is fairly large, so and for a very large range of frequencies it will be, and it only asymptotically tends to 1 for these high values of, so approaches this black hole limit from above. So we think that in this range of frequency these Rmax by they quickly fall towards unity, and the compactness of the quark star is extremely high, very high, but it cannot become a black hole even in the limiting case. So thus both these objects, like the strange quark stars and black holes, they have to be considered together as candidates of cold dark matter in some models, and their phenomenologicals are may not be significant to distinguish between. But their signature in the gravitational waves may be an interesting aspect of study, which is in the future. So this is what we observe for variation of the nu max versus the back constant, almost linear relationship. Okay, so this is more or less what I wanted to say about the rotating quark stars in general relativity in the context of analytical model building. And we have seen that even if we take very simple assumptions, we reach realistic values for both the static quark star as well as the rotational quark star. And as a side effect, we get a glimpse of the underlying mechanisms of confinement. For example, the value of 136 GeV to the power 4, which we have found by minimizing the chi-square. So this tells us about the states of matter which we may not find sufficiently quickly in a laboratory setup. So we conclude that by saying that in this work, we have studied the limiting mass for the rotating quark star in an analytical framework. This limit mostly depends on the universal constants and the back parameter, as well as the angular velocity of the star. This dependence is there. And the maximum possible observed frequency is also estimated, which agrees with all recent observations as well as with numerical simulations. So one firm conclusion is that a quark star can never behave as a black hole. So with this, I come to the end of my talk, and I thank my collaborators, Professor Shibaji Raha, Professor Sanjay Ghosh, and Mr. Ashadul Haldar. And I also thank the BI CAPSS Physics Group chapter of the BI Research Scholar Forum for this wonderful seminar opportunity and propagating the vibes of physics. May you continue in your effort and be more successful. Thank you.
Thank you, sir. It was a really wonderful lecture. We all enjoyed it very much. Now let us start the question, answer and discussion session. So I would request the audience, if you have any question, you can ask sir.
I have a question, so if I may ask.
Yeah.
First one is the back constant you are using here in this model. So this back constant is the model, it's a model parameter, right?
Yeah, it's the back constant of the MIT bag model of confinement.
So when we say that there is a range of values for the back constants, and then for a particular value of back constant, the chi-square is coming as minimum. So I didn't quite get what that plot is saying us. Firstly, I didn't get why there are various ranges of value for this for this back parameter, and secondly, coming for a particular bag value, the chi-square minimum, does it mean this model works the best for that particular bag value, back constant value, or maybe if you can elaborate it a bit.
Yeah, sort of like that. Actually, these values of the back constant, it is not known very well. So whatever people try to determine the value of the back constant by fitting the masses of heavy nucleons, which is found in the accelerator data. And there is therefore a range of these values depending on the experimental setup and so on. So these basically is a matter of the interface between nuclear physics and QCD. So while these laboratory experiments, they give us a range of values, in here we have an opportunity to test that in a cosmological scale. So when therefore we generate for various values of the back parameter value, the various values of the confinement, we generate the masses, and then we take recourse to the observational data. Then observe and let the observational data do the selection for us. So this is how it is.
So this is like giving the most probable value of back constant using this model.
Yeah. So this just gives you a glimpse of the things if you do perform the experiment not in a terrestrial laboratory, but using the cosmological data.
Okay. I have another question, that is when we talk about that using this back constant, we are talking about in this model we didn't include any proper interactions of which the quarks are going through, or it is all enveloped within this back constant
just that, and that generated the confinement through the inverse dependence on the density. That is the essentially the most simple ingredient that we have put into it. We have not got into the engineering of a specific equation of states which these quarks will follow and so on. Well, obviously these have been worked out in detail, and there have been a lot of numerical investigations using specific models. What is surprising is that these values come very close to these values without these additional assumptions.
Okay, thank you, sir. Thank you. That was a very nice talk. Thank you.
Okay. Thank you very much.
Can I ask a question?
Yeah. Oh, yeah.
Shivaji, it was a nice talk. So actually, you have shown some model data, right? Output of some model. So is there any experiment or some data which are trying to match this values?
Yeah, the data comes from the pulsar databases which have been recently investigated. So these are the experimental data points, and these are the pulsar data set. And these are the analytical results. So we have selected so that we basically the high pulsars with high spin rates, which come to this 1 millisecond limit.
Okay, so that means those data points are matches with your model.
These data points match with a specific value of for a specific value of the back constant, not for the others, which might also be an hint. Yeah.
Okay. Thank you.
Hello, this is Shahak, if I am allowed to ask one. Can you hear? Yeah. Thank you, sir, for this wonderful talk. But I have a confusion regarding the thing how to differentiate between a neutron star and the quark star. Maybe you have explained, but if you can explain it once more, then that will be helpful for me.
Well, a neutron star is formed out of a supernova explosion. And in that, whenever a neutron star forms, basically there are two kinds of effects: the degenerate neutrons holding up against the gravitational force, plus the strong nuclear interactions. But these are strong nuclear interactions. These are not the interquark interactions. Still the neutrons are trapped within their hadronic bags. So that is a neutron star. In a pure quark star, the quarks, so compact that the hadronic bags have overlapped, and there is partial overlap, plus most probably they are existing in the asymptotically free region, where that whenever we try to make these quarks approach each other, the energy increases, and it is that region in which they are free. So this is composed of a very entirely different kind of matter. It is not the neutron degeneracy pressure plus strong nuclear forces, but the agencies which generate the strong nuclear forces are operating at their bare potential.
Okay. And another question would be: so, do you have any star that could be tagged as a quark star? Any data on that could be tagged as it is not it can be called as a quark star itself?
Yeah, there we have identified. These are several candidates. Actually, that is the problem, that we have some candidates. It is difficult to tell from just their spinning rates and their masses that whether they are neutron stars or stars with a quark core. So that is what we are thinking about, whether maybe gravitational wave signatures or others, they would be able to shed more light on it.
Okay, sir. Thank you.
Thank you very much.
I have another question.
Are there any other
yes,
questions?
Shreya, may I ask?
Yes.
Yes.
Okay, maybe after Kinkota.
No, Prachita, please go ahead.
Okay, so one just starting question: Can we see this quark hadron phase transition kind of scenario inside this quark stars, and if it's then in which will be the scenario when we can see this?
If a quark star develops from a neutron star, then obviously there would be a point of time in which these quark hadron phase transitions would have happened. But if the star generates by, say, for example, accumulating strangelets and so on, then there is no need for the specific quark hadron phase transition. But obviously there would be the phase transition when these say if the strangelets are incident, their boundaries would dissolve, and that would be a phase transitions of some kind. There are two different scenarios in which one neutron star is converted to a quark star, where we would definitely observe signatures of the quark hadron phase transition. And if there are these pure quark stars, which we have modeled over here, then the signature would not be found. The phase transition would have already been over.
Okay, thank you.
Kinkar.
Sir.
Yeah.
It's a long time that I'm hearing again from you, sir.
Nice to see you again also here. So many faces. Yeah.
Thank you so much, sir. And I think there are some of the students from our batch here also, like Obik, I think Shomojit is also here.
Shomojit, okay, yeah.
So I have a few questions, sir. One of your slides, you showed that you said that formation of quark starts by clumping of matter falling under gravitational interaction and then forming a quark star.
Yeah.
So
that is a possibility.
Sir, can you please elaborate on that, clumping of matter falling under gravitational interaction and then coming under the strong interaction part to form a quark star?
Yeah.
Maybe this is more like a philosophical question.
No, this is not a philosophical question at all. So essentially, in another work, we have considered that kind of thing. Now, what we have considered there is that after the QCD phase transition in the universe at the millisecond era, the survivability of quark nuggets and such. Now then, we have seen that the radiation pressure keeps them separate up to a time period of about a second, which is also incidentally the neutrino near the neutrino decoupling time. And then these radiation pressure is no longer sufficient to prevent them from accumulating together. And when they accumulate, what happens is when they basically accumulate together, the nucleonic boundaries dissolve, and the hadronic and these quark, the quark matter directly passes into the quark matter phase. So there is no reason for phase transition over here. But what happens is that the object becomes more stable because more fermionic levels are available, and it just increases its mass and we have wondered why, to what limit. And then we have come up to this work, and we have seen that, well, if there is a limit, they will stop growing beyond that limit, and then if it still absorbs matter like that, then it is going to explode, and it is going to give a fragment. And you know that Shayan have done very nice work on the statistics of these fragmentation scenario.
Okay. So under these circumstances, do you consider any effect of magnetic field?
We have not considered any effect of magnetic field. That we have considered, well, I think Ashadul is also in the audience, if we able to say that. Well, we were trying to see whether the magnetic field is significant or not, or whether it would be generated and so on. We have not come to a definite conclusion. We were thinking about it.
Okay. So, in your opinion, sir, I'm just asking very generally, in your opinion, since you are talking about the Fermi energy level and all, how do you think it is going to affect the energy levels if the presence of magnetic field is considered?
Well,
how it can be considered and all?
Yeah, though, so the first thing that the magnetic field would effectively induce, these magnetic fields are very high, so they would induce further splitting in the level.
Right. Uh, Definitely. I mean, that is for sure. But I
So,
mean, in your
actually,
model,
yeah, so what can happen is that the star can actually, contrary to the whatever is the common sense is telling us, the star can become more compact due to the presence of this magnetic. That is what I think. This is not what I want to communicate officially. We have been just thinking about it.
okay, okay, okay. And how strange matter can play a role in all this scenario?
Yeah,
I mean,
the strange matter is actually essential. You see, because if you have only up and down quark matter, then it has been shown that they are not stable. Well, they're not relative to nuclear matter. Only when you add this additional Fermi well due to the presence of the strange quark, then this becomes more stable than ordinary nuclear matter.
okay. Maybe
And obviously, in this, then we have to also this model can be well modified. We have actually done that. So you can introduce for the up and down quark matters. We can introduce this zero mass and continue with. But if you want to introduce the strange quarks, then these Fermi levels will be shifted up by the masses of the strange quarks because these are significant. So it is not very sensitive to it, but in this simple discussion, I didn't want to include this effect.
Okay. Okay. So, I mean, by any chance, is it possible to give us a flavor, or can you please show any plot? Do you have? Is it available to you? I mean, can you get any flavor of effect of strangeness on top of up and down?
I do not have any plots or anything available right at my hand because see that well, what we also know what we essentially do these days. Very difficult for me to get something right out of my hand right now. Sorry.
Okay, no problem, sir. No problem. One more thing, sir. You said that neutron star and just a minute, sir. Okay, you said that neutron star is coming under gravitational bound, and quark star, which is defined to fall under strong interaction.
Right, right.
So, by what stretch we can approximate to apply QCD for the case of, say, neutron star?
Yeah, I think one can make an estimate, and along the same lines. I know that it has been very long since I have been teaching you in post institute and so on, but there we have made, if some of you would remember, we have made an estimate of when from which mass limit an object can be considered to be gravitationally bound compared to the solid state binding. I think it can be done by a simple kind of a similar kind of an estimate, the limits and so on. So this is also what I have not done out in detail or something, but it can be done. It can be attempted, with not a lot of difficulty.
Okay. Okay. So can you please go to slide number 11?
Okay, slide number 11. Right. Yeah.
This is 10, sir. Oh, sir, this may be a very silly question. Maybe I have missed something on it. You said, I mean, this frequency in the x-axis, that is the observed frequency, which is redshifted in terms of the observer.
So no, this is not redshift. This is the frequency. One curve corresponds to the observed curve. This is the one which is redshifted, and this is the other one. Yeah, and the dotted dashed line, red line. This is the actual frequency. This is the redshifted.
This is the redshifted one. Right. This may be a very silly question, sir, but for one frequency, one can observe two mass. Is there any implication associated with?
Actually, you see, this is the observed frequency. Well, the actual frequency doesn't show any such kind of dependence.
Exactly.
Yeah, whatever it implies is that the observational scientist will be confused, might be confused.
Okay. 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 And slide number 13, just one cross check, sir. Slide number 13, right, sir. So the minima at 136, you said it is the minima is around 136 GeV to the power 4. Is it GeV to the power 4 or MeV to the power 4?
Sorry, not GeV to the power 4. If I have said that, I was in error. It's MeV to the power 4.
Okay. Thank you so much, sir. That's all. I mean,
thank you very much.
And it is like refreshing memories.
Yeah, very refreshing, and also, well, these questions, well, they are also brings me very refreshing memories from very old days. For all of you.
Thank you so much for interacting with us, sir.
Thank you very much for attending so closely, asking so many interesting questions, and filling my afternoon with joy. Thank you all.
Thank you so much.
Thank you, sir. So, if there are no other questions, we shall close today's episode. And thank
Shreya,
you to all the audience.
Shreya, can I interrupt a little bit?
Yes,
so
sure.
If there is no more question from any of the participants, sir, with your permission and with the permission from the organizers, I do not want to miss this opportunity to wish Shibaji sir a belated happy birthday in presence of everyone.
Yeah, not a very appropriate forum for that, but thank you.
Yes, sir, belated happy birthday from the whole CAPSS physics group as well.
Yeah, Kinkor, you would get something from me for puncturing the balloon in this occasion, but obviously, thank you very much for the wish. I wish that all your days will be filled with joy and all, because you have wished me so heartily. Thank you.
Thank you so much, sir. In fact, I was waiting for this talk to wish you a happy birthday, belated happy birthday, maybe.
Yeah, I feel. Yeah.
Okay. So once again, thank you everyone, and thank you, sir, for your such a nice talk. So I think it is time. Then we will close the episode. Is it?
Yeah. Okay. So thank you everyone.
Thank you.